Okay, so let's start off with a seemingly impossible question. How can we possibly measure what our eyes literally cannot see? Think about the materials sitting right around you, the water in your glass, the semiconductors inside your smartphone, all those complex organic compounds out in nature. They all hold these hidden chemical secrets. And to uncover them? Well, we have to look far beyond the limits of our own biological vision. Welcome to This Explainer. Today, we're going to completely demystify how scientists use both invisible and visible light to reveal the hidden secrets of the chemical world. We're looking at a wildly powerful analytical technique known as Uv-Vis spectroscopy. By the time we wrap up, you'll understand exactly how simply bouncing light through a sample can tell us precisely what's hiding inside it. So, here's our roadmap for today. We'll be shedding light on UV-Vis, diving into the science of absorption, decoding the Beer-Lambert law, taking a look inside the spectrometer itself, and finally exploring some real-world applications. Let's get right into it. Part 1. Shedding light on UV-Vis. We need to begin our journey by defining exactly what this powerful analytical tool is all about.
At its core, UV-Vis spectroscopy operates in a very specific, narrow window. We're talking about measuring light absorption and reflectance in the 200 to 800 nanometer range. That covers the ultraviolet region and the full, adjacent visible spectrum. Now, for this to work, your sample has to be a chromophore. That's just a fancy way of saying it contains parts of a molecule that naturally absorb specific wavelengths of light. When we shine a broad range of wavelengths through that sample, the instrument checks exactly how much light gets absorbed. The result? A unique absorption spectrum that helps us identify and quantify the exact compounds we're dealing with.
Moving right along to Part 2, the science of absorption. Let's zoom way into the micro level to see what actually happens when a photon of light crashes into a molecule.
Down at the quantum level, molecules don't just soak up light randomly. No way. They absorb highly specific photon energies. When a molecule absorbs this energy, its electrons literally jump. They leap from a lower energy orbital up to a higher one, for example, in what chemists refer to as a pi-to-pi star transition. But here's the catch. For this jump to even happen, the photon's energy, which is governed by Planck's constant, has to perfectly match the energy gap between those electron orbitals. Think of it kind of like a key fitting perfectly into a lock. If the energy is in a perfect match, the light just ignores it and passes straight through.
When you look at a thin film sample and see those crazy, vibrant colors, you're not just looking at pigment. Those colors are the direct result of the material's unique structural and molecular properties interacting with light. The molecules are absorbing certain wavelengths from the visible spectrum and reflecting others back at us. And that is exactly where the whole idea of color and absorption comes into play. By precisely measuring which wavelengths are absorbed, we can effectively fingerprint the molecule.
Which brings us to Part 3, decoding the Beer-Lambert law. Because, we have to translate these quantum leaps into actual mathematical rules.
How do we take a missing wavelength and turn it into hard, usable data? Well, first we have to distinguish between two key concepts, transmittance and absorbance. Transmittance is just the ratio of light that successfully makes it all the way through your sample. Absorbance is the fraction of light that gets eaten up or absorbed along the way. The Beer-Lambert law tells us that this absorbance is directly proportional to two things: the concentration of the absorbing species in your solution, and the length of the light's path, basically how thick your container is. It's a beautiful linear relationship. If you double the chemical concentration, you double the absorbance. Simple as that.
But, the law isn't totally perfect. There are definitely conditions where this beautiful linear relationship completely breaks down. For instance, if your sample is too concentrated, usually anything above 0.01 molar, the molecules get too packed together, and their electrostatic interactions start messing with the absorptivity. You also lose that linearity if you've got floating particulates causing light scattering, or if your light source isn't perfectly monochromatic. Plus, you always have to be on guard for stray light sneaking into the instrument. This is exactly why meticulous sample prep is an absolute must.
All right, Part 4. Inside the UV-Vis spectrometer. We know the physics, we know the math. Let's open up the black box and look at the actual hardware. Following the literal path of the photon, the setup is actually quite elegant. First up, the light source. This is often a tungsten filament if you need visible light, or a deuterium arc lamp for a continuous blast of ultraviolet. Then that light hits a monochromator, like a prism or a diffraction grating. This acts as a highly specific filter, separating the light so only a single wavelength advances at a time. Next, that lone wavelength passes through the cuvette containing our sample.
And finally, whatever light manages to survive the journey hits the detector, usually a photomultiplier tube or a CCD, which translates that physical light intensity into the digital data on our screens. Now, you'll generally run into two main architectures for these machines, single beam and double beam. The real difference is how the light is directed before it hits the detector. In a single beam model, there's just one path. You have to load a blank solvent first to establish a baseline, physically take it out, and then load your actual sample. A double beam setup, on the other hand, is pretty clever. It uses optics to physically split the light beam in two, sending one half through your reference solvent and the other half through your sample at the exact same time. It's fantastic for real-time, highly accurate readings.
Oh, and speaking of the sample holder, this is a super common trap for beginners. You cannot just use any old container. It is absolutely critical to use quartz or fused silica cuvettes when doing UV testing. Why? Because standard glass or plastic actually absorbs ultraviolet light. If you used a plastic test tube, it would absorb the UV rays before they even had a chance to touch your sample, completely trashing your data. Quartz, thankfully, remains perfectly transparent throughout both the UV and visible regions.
But what if your sample isn't a liquid? Enter specialized hardware, like the awesomely named Praying Mantis Diffuse Reflectance Accessory. You use this blocky piece of gear when you're dealing with crystalline powders or pastes. It uses two massive hemispherical mirrors to gather light reflected off incredibly tiny volumes of material. We're talking as small as 0.03 milliliters. This lets researchers capture highly precise optical data on totally new, ridiculously expensive, or super scarce compounds.
And finally, Part 5, Real-World Uv-Vis Applications. Let's see how all this physics and engineering actually impacts our daily lives.
What makes Uv-Vis so incredible is its sheer versatility. On one hand, you have academics analyzing cutting-edge metal oxides in a sterile lab, and on the other hand, it scales massively. We're talking huge industrial setups, monitoring environmental sustainability and public health. It's the exact same fundamental physics, just applied to entirely different challenges.
Take public health, for example. In a world dealing with climate change and a booming population, safe drinking water is absolutely paramount. Modern water treatment plants actually use real-time UV-Vis spectroscopy straight in the water flow. By using specific photodiode filters targeting exactly 220, 254, and 275 nanometers, these facilities can instantly detect harmful pathogens, monitor cloudiness, and spot organic compounds. And they do it continuously without ever having to haul a sample back to a lab and without contaminating the water itself. It's a real game changer.
Switching gears to high-tech manufacturing, UV-Vis is literally the backbone of modern material science. In the semiconductor industry, knowing a material's electronic structure is everything. Calculating the bandgap energy, which is the amount of energy it takes to kick an electron into a conductive state, is totally vital for engineering optoelectronics and next-gen solar panels. Also, by analyzing the interference patterns of light reflectance, UV-Vis can map out the exact thickness of microscopic thin films on semiconductor wafers for quality control.
So how do we actually find that bandgap energy using our UV-Vis data? We use a brilliant mathematical tool called a talk plot. Once scientists get the diffuse reflectance spectra of a powder, maybe using that praying mantis accessory we talked about, they calculate the Kubelka-Munk function and plot it against photon energy and electron volts. Notice how that curve for titanium dioxide drops off super sharply? By taking the linear portion of that curve and manually drawing a straight line down to intersect the x-axis, researchers can pinpoint the exact bandgap energy. Now, if drawing manual lines isn't precise enough for you, and let's be honest, we usually want the software to handle the heavy lifting, you can use linear regression. By applying linear regression or calculating the first derivative of the wavelength scan using built-in software, researchers can find that exact peak mathematically. When it's done correctly on a high-end spectrophotometer, these calculated values match up perfectly with established literature, proving that your newly synthesized batch of zinc oxide or germanium dioxide is structurally flawless. Of course, in the lab, things don't always go according to plan. If your transmission rates are too low and your readings are failing, the most common fix is surprisingly simple. Just reduce your sample concentration. Remember the limitations of the Beer-Lambert law? A super concentrated sample is just going to scatter the light. Also, double-check your hardware alignment. If you're measuring a thin film, it has to be perfectly perpendicular, exactly 90 degrees to your light source. Oh, and if you're running a long test, watch out for evaporating solvents. Evaporation will slowly increase your sample concentration over time and totally ruin your data curve. We've seen how tracking just a single photon can reveal an entire hidden chemical world, from guaranteeing the purity of the water we drink to mapping the band gaps of the solar panels that will power our future.
As we wrap up this explainer, it kind of leaves us wondering, as our tools get more precise and our software gets even smarter, what other invisible mysteries of the universe could be solved simply by shining a light on them? Keep exploring, and I'll see you in the next explainer.